Morning. Today I am going to discuss about last type of ADC technique, which is nothing but successive approximation ADC technique. Here I am going to represent the block diagram of successive approximation ADC. The successive approximation ADC uses very efficient searching code strategy, which is called as binary search, and it completes its searching process for n-bit binary data. It completes in n clock periods. For 10-bit binary data, it completes in 10 clock periods. For 3-bit binary data, it completes its searching process by 3 clock cycles. And it consists of two control signals. Those are SOC and EOC. SOC is nothing but start of conversion, and EOC is nothing but end of conversion. And these control signals are used to indicate whether we are going to start or whether we started the ADC and we stopped the ADC operation. For the starting of ADC, SOC signal is activated, and for the ending of ADC, the EOC signal is activated. That means if EOC signal is activated, that indicates the end of conversion, and if SOC signal is activated, that indicates it starts the conversion process. And coming to the block diagram of successive approximation technique, it consists of comparator here, which is representing the comparator, and successive approximation register, and last but not the least is DAC, which is nothing but digital to analog converter. And coming to the successive approximation technique, the searching of the binary code is similar to the searching of unknown weight with the balanced scale and set the standard weights, which is nothing but the successive approximation. What I am going to tell you is the successive approximation ADC is similar to the finding an unknown weight with the balanced scale and set the appropriate value. And here I am going to be used the balanced scale as DAC and comparator. And the successive approximation register consists of values. Some values, those are 1, 2, 4, so on like that. And for the explanation of this ADC technique, I am going to explain with the help of an example. Initially, we are going to take the SOC signal as well as EOC signal. Why we are considering those two signals are for the starting of operation, the SOC signal is representing, and the ending of operation, the EOC signal is representing. First, I am going to represent the waveforms. Okay, first I am going to take the start of conversion. So whenever it is activated, that indicates the conversion is started. And EOC signal, what about the EOC? Whenever it activates, then it indicates the end of conversion. So EOC is activated here. Okay, and next time period. Okay, time pulses. Here I am going to explain this successive approximation for 3-bit. So for the searching of binary code for the 3-bit value, we require 3 clock cycles. Okay, so here I am considering 3 clock cycles, 1, 2 and 3. After that, EOC is activated. That indicates the end of conversion is happened. For that we are going to take these three waveforms. Okay, now I am going to consider the external clock input to set the internal timing parameters of SAR, which is nothing but successive approximation resistor. To set the internal timing parameters of SAR, we are going to be used the external clock signal. Okay, so first what I am going to do is I am going to apply an input voltage, which is nothing but analog input voltage at one input of the comparator. After the SOC is activated, then SAR sets 3-bit binary value sets as an input of the DAC. DAC accepts that 3-bit binary value and generates an equivalent analog value for that 3-bit binary input and generates an analog value, and which will be applied as another input of the comparator, and the comparator compares those two inputs, and this process is continued until the number of bits conversion. That is, if I am going to be consider 3-bit value, so this process is operated for 3 clock pulses. If I am going to consider 10-bit values, then this operation is continued for 10 clock cycles. After the completion of that time period, then EOC signal is activated, and we are going to collect the digital output at the output of SAR, which is nothing but the successive approximation ADC. Here I am going to explain the operation of successive approximation ADC with the help of an example. Okay, so here I am going to consider my VI input voltage will be equal to 5.2 volts. Yes or no? So if my VI is greater than 4 volts. Why I am considering it as initially I am treating the output of the SAR will be 100. Analog equivalent value will be equal to 4 volts. So if my input is greater than 4 volts, how can you identify whether it is greater than 4 volts or it will be less than 4 volts? For the 3-bit binary values, we are having B2, B1 and B0, and B2 is the most significant bit and B0 is the least significant bit. So here whenever B2 is equal to 1, then it indicates yes, that means my input is greater than 4 volts. So it indicates no when it represents it as no when B2 is equal to 0. So what happened for this? See this one. What happened in this case is when VI is less than 4 volts, then it may be VI is greater than 2 volts, or when if VI is greater than 4 volts, then it will be VI is greater than 6 volts. So first I am going to explain this operation. I am assuming my VI is greater than 4 volts. First, in the first clock time period, I completes my search for B2 bit. After that, in the second clock period, I am going to search the B1 bit. After that, in the third clock time period, I am going to search the least significant bit. So, when VI is greater than 6, once again the same process. If no, then B1 is equal to 0. So, and if yes, when B1 is equal to 1. So what happens? VI is greater than 5 volts and VI is greater than 7 volts. Okay. Now once again here that means B2 search is completed and here B1 search is completed. Here B1 search is completed and here B0 search is going to be complete. Again at this we are going to get yes, B0 is equal to 1, no, B naught is equal to 0. Similarly, here also, if it is no, B naught is equal to 0. If it is yes, B naught is equal to 1. So, what happened for this? 1, 0, 0. And what happened for this? 1, 0, 1. And what about this? 1, 1, 0. And what about this? 1, 1, 1. So, here we are getting 4, 5, 6, 7. Similarly, the searching process is applicable for here also. So, after that, we will get the exact digital value at B1, B2, B3, so on up to Bn. So finally what I want to conclude is, by using this process we are going to get the analog to digital value. You have to remember is the time period of the analog to digital conversion is depending upon two factors. One is TC is equal to, that means the total time conversion from analog to digital is TC is equal to T into N plus 1, where T is nothing but the time period and N is nothing but the number of bits, and if N is equal to 3, we require 3 clock pulses. If N is equal to 10, we required 10 clock pulses. Okay, that's it for the successive approximation technique. By using this technique, we are going to calculate the equivalent digital value for the applied analog input voltage. Coming to the performance parameter specifications of DAC, there are 9 performance parameter specifications for DAC. Those are resolution, accuracy and settling time, dynamic range, offset error, gain error, non-linearity error, and last but one is stability, last one is monotonicity. Now we are going to discuss individually about all these performance specifications of DAC. Coming to the first one, resolution. Resolution is defined as the number of different ways of analog outputs for the digital inputs is represented as resolution, and the resolution will be expressed as resolution will be equal to 2 to the power of n. Suppose if n is equal to 3, then the resolution will be equal to 8, and the resolution is also expressed in another way. How can you express the second way of resolution? It is nothing but the ratio of change in the output voltage to the change in 1 LSB of the digital input is also representing as resolution. So R will be equal to V naught of VOFS, output full scale voltage, divided by 2 to the power of n minus 1. This is another way of representing the resolution. Once we know the resolution value, then we can easily calculate the relation between input voltage and output voltage. So output voltage of the DAC is equal to resolution into decimal equivalent of the digital value. Decimal equivalent of the digital value. With that we can calculate the output voltage, okay, which is nothing but the output and input relation. By using this formula we can calculate the relation between output and input, and these two are the different ways of expressing the resolution. And coming to the next one, which is nothing but accuracy. Okay, accuracy is nothing but the comparison of actual output with the expected output, which is nothing but accuracy. And always the accuracy will be represented in percentages, and the accuracy is represented as accuracy is equal to VOFS divided by 2 power n minus 1 into 2, which is nothing but accuracy. Coming to the settling time. Settling time is also called as conversion time. The time required for the DAC output to 90 from 0, okay, which is nothing but the settling time. Generally we are going to consider the settling time as 15 nanoseconds to 10 microseconds, and the settling time is depends upon word length and architecture of the structure. Settling time, and it is also called as conversion time. The time required for the DAC output to 90 from 0. That is, the digital input is changing from 0 to the full scale value, which is nothing but all ones, which is called as settling time or conversion time. Now coming to the fourth one, which is nothing but dynamic range. The dynamic range is defined as the ratio of maximum output voltage to the smallest output voltage excluding 0, which is called as dynamic range. And always the dynamic range is expressed in decibels, and the dynamic range is equal to 20 log of 2 to the power of n, which is nothing but dynamic range of DAC. And next, coming to the fifth one, which is offset error. Okay, offset error. How can you express the offset error? The non-zero output voltage of current to voltage converter when both the input voltages are 0, which is called as offset error. Once again I am telling you the definition of offset error for the DAC. The non-zero output value for the current to voltage converter when both the inputs are 0, and a constant output value will be added to all the output voltages. Here I am going to represent the graphical representation. Okay, here it will be taken as 1 by 8, and it is 2 by 8, 3 by 8, so on up to 7 by 8. And here it is ideal value. Okay, and for the offset error, so this portion is called as offset error, and this offset error is generated because of offset voltages of op amp. Coming to the gain error. Gain error is nothing but the difference between the calculated gain versus actual gain achieved, and the calculated gain is achieved by using the current to voltage converter. Okay, so here I am going to represent the gain error. Okay, here it is 1 by 8, once again 2 by 8, so on up to 7 by 8, and this is the ideal gain, and which is nothing but the calculated gain. So finally what we are going to conclude is the gain error is nothing but the difference between the calculated gain by using current to voltage converter and the actual gain. This gain error is occurred because of the errors in the feedback resistors. Next one is non-linearity, which is also called as linearity error. Ideal DAC is linear. That means it produces the output voltage corresponding to the input code. But practically, the DAC output differs for the ideal one, and because of two factors it differs the output of ideal one with the practical one. Those two factors are non-identical resistor values and non-electrical switches which produces the resistance to the circuit. And two types of non-linearity errors are: one is differential non-linearity error and the second one is integral non-linearity error. Next one is stability. The performance of a converter depends upon temperature, supply voltage changes or power supply variations and age, and the relevant parameters like offset error and gain error and nonlinearity error and monotonicity are specified over the full temperature and power supply ranges, and these parameters are representing the stability of the converter. Last one is monotonicity. A converter is said to be a good monotonicity if it does not misses any step backward while it is stepping through its entire full range by a counter, which is nothing but monotonicity. These are the performance parameter specifications of DAC.